These are the top 15 new discoveries made by quantum computing. 15. Accelerated discovery of next-generation energy storage materials. What if 20 years of battery research happened in a week? Microsoft's Azure Quantum Elements, working with Pacific Northwest National Laboratory, screened 32.6 million possible materials for solid-state batteries. They narrowed that down step by step to just 18 top electrolyte candidates in about a week, using traditional density functional theory methods. That kind of screening would have taken roughly 20 years. So one leading candidate reportedly uses about 70% less lithium while still maintaining high conductivity. And that matters because lithium supply is already tight globally. I mean, this isn't hype. It's about reducing search time from decades to days. And that changes how fast energy innovation moves. 14. Quantum efficient models for fusion-relevant physics. Fusion simulations are massive. Classical 3D inertial confinement fusion models can take millions of CPU hours and up to 30 days to complete a single run. Researchers developed a quantum partial differential equation algorithm that provides a quadratic speedup for radiation hydrodynamic simulations. It's also been extended to nonlinear systems. In simple terms, as the problem gets bigger, quantum methods scale more efficiently. National lab collaborations showed key plasma and material interactions tied to sustained fusion can be modeled more efficiently using quantum approaches. Fusion itself isn't solved, but the way we simulate extreme plasma physics is evolving, and simulation speed often determines research speed. 13. Foundations for simulating human drug metabolism enzymes. Drug metabolism happens at the quantum level, but we've mostly modeled it with classical shortcuts. Quantum algorithms on photonic hardware achieved reported speedups of 234 times and 278 times compared to classical methods when calculating electronic structures of cytochrome P450 and FOMOCO. These are complex biological systems central to drug processing and nitrogen fixation. Separate quantum-informed AI tools have simulated systems with up to 1 million atoms over nanosecond timescales while keeping quantum-level accuracy. Some modeling tasks ran around 1,000 times faster than traditional methods. For the first time, full quantum-scale drug metabolism simulations are becoming computationally realistic. 12. Quantum-enhanced insight into drug-target bond formation. Now, imagine compressing the drug discovery funnel, a hybrid quantum classical pipeline targeting KRAS oncology compounds generated more than 1 million candidate molecules. That list was narrowed to 15, and some were experimentally validated. KRAS has been one of the toughest cancer targets in medicine. Researchers also used variational quantum algorithms to simulate an mRNA sequence of 60 nucleotides, showing progress in modeling biological macromolecules. Quantum-informed molecular models have demonstrated speeds up to 1,000 times faster than traditional approaches while keeping quantum accuracy. It's not about replacing labs. It's about shrinking the search space, and that shift can change timelines. 11. Prediction of exotic ultra-hard carbon phases. Diamond might not be the hardest form of carbon anymore. Large-scale simulations on the Frontier supercomputer, using machine learning models trained to quantum-level accuracy, predicted a body-centered cubic carbon phase called BC8. It's estimated to be about 30% more resistant to compression than diamond and stable above 10 million atmospheres. To form it, diamond would need to be melted and shock compressed to roughly 12 million atmospheres and about 5,000 Kelvin. These simulations involved billions of atoms. This expands carbon's known phase diagram, and it shows how quantum-level modeling can reveal structures nature hides under extreme conditions. 10. Discovery of new material candidates via quantum ML workflows. Now, zoom out from one material to millions. Google DeepMind's genome system generated 2.2 million crystal structure predictions and identified over 380,000 potentially stable materials. Scientists have already synchronized 736 of them in labs. At Berkeley Lab, the Autonomous Lab synthesized 41 out of 58 targeted materials in just 17 days. Around a 71% success rate. Some autonomous labs now produce more than 2 new materials per day. The breakthrough isn't just new compounds. It's a new way of exploring material space faster than traditional high-throughput screening alone. 9. Unexpected behavior in error-corrected quantum phases. Quantum computers only matter if errors are controlled. Quantinuum used 30 physical qubits to create 4 logical qubits with an error rate about 800 times lower than the underlying physical qubits. That's roughly 1 error in 100,000. Compared to 1 in 100. They ran around 14,000 experiments without uncorrected errors. What surprised researchers wasn't just the lower error rate. Simpler logical encodings sometimes outperformed more complex theoretical designs. That challenges assumptions about how protected quantum information behaves under noise. And error correction is the gatekeeper to large-scale quantum systems. 8. Ultra-fast, physically verified quantum randomness. Random numbers sound boring until you realize encryption depends on them. A photonic chip-based quantum random number generator produced more than 20 gigabits per second of secure random numbers. Earlier systems produced about 2.9 gigabits per second. These devices rely on measurable quantum fluctuations, not algorithmic tricks. The randomness comes from intrinsic quantum noise. The result is faster entropy generation in smaller, more energy-efficient hardware. It's not flashy physics, but secure randomness underpins digital security, financial systems, and communications. This pushes the physical limits of how fast verified randomness can be generated. 7. Verified quantum advantage in a real many-body physics problem. This is where things get serious. Google's Quantum Echoes algorithm measured out of time under correlators on 105 qubits. It ran about 13,000 times faster than classical algorithms on one of the world's fastest supercomputers. In another case, measuring a second-order correlator using 65 qubits would have required roughly 3.2 years per data point on the Frontier supercomputer. On quantum hardware, it took about 2 hours. This wasn't a toy benchmark. It involved real magnetization properties in two-dimensional quantum systems. That's one of the clearest demonstrations of quantum advantage tied to meaningful physics. 6. Dynamical phase transitions in random quantum circuits. Now, imagine phase transitions, but not in matter. Experiments reported in Nature observed dynamical and noise-driven phase transitions in random circuit sampling. As entanglement grows, complexity shifts, and noise increases, the system switches phases. This means quantum computation itself can exhibit phase transition behavior. Similar in concept to water freezing or boiling, but in information space. Researchers saw distinct regimes governing entanglement growth and computational complexity. It revealed structure inside quantum circuits that wasn't fully understood before. And it reframes quantum processors as systems with their own physical phases. 5. Direct simulation of realistic magnetic materials. This one connects back to Richard Feynman's original idea of simulating nature with quantum systems. Quantinuum digitally simulated a 7x8 lattice, 52 qubits total, using more than 2,000 2-qubit gates to study Floquant pre-thermalization in a two-dimensional spin system. The system remained stable at sizes and timescales beyond practical classical reach. Researchers extracted a diffusion constant of about 0.38 directly from experimental data. This wasn't abstract math. It was controlled simulation of magnetic dynamics that classical machines struggle to scale. That's quantum simulation, doing what it was originally meant to do. 4. Previously forbidden quantum material states. Now we're in exotic territory. Rhombus stacked 5-layer graphene devices produced fractional quantum anomalous Hall states with conductance values of 5/9 and 5/11 of an electron charge. Electrons flowed along the device edges with zero resistance, and this happened without an external magnetic field. The states emerged at temperatures below 40 millikelvin. These findings challenge long-standing assumptions about how electrons organize in solids. It expands the known taxonomy of quantum materials and pushes the boundaries of what correlated electron systems can do. 3. High-resolution mapping of quantum Ising magnetism. For decades, quantum magnetism at scale was mostly theoretical. A 256-atom programmable quantum simulator mapped the dynamics of quantum Ising magnetism in high resolution. Researchers tracked how magnetic domains form, evolve, and collapse in two-dimensional systems. This provided a direct experimental window into non-equilibrium quantum magnetism at scales classical computers cannot realistically resolve. Instead of approximations, scientists observe domain behavior in real time on programmable hardware, and that's a different level of visibility into quantum phases of matter. 2. New topological phases using programmable atom arrays. Programmable atom arrays, especially Rydberg atom systems, achieved high-fidelity control over dozens of atoms and demonstrated exotic phases like stripe and plaquette orders. These are topologically ordered phases beyond traditional symmetry breaking descriptions. While specific statistics weren't detailed in the research window, the experiments confirmed phases that had been mathematically predicted but not physically observed before. This is about discovering new organizational principles of matter, not tweaking old ones. 1. First experimental realization of a quantum spin liquid. And finally, a 50-year-old prediction confirmed. In a 219-atom Cagon array experiment reported in Science, researchers directly measured topological order in a quantum spin liquid. This confirmed a long-standing prediction made by Philip Anderson in the 1970s. Quantum spin liquids are states where magnetic moments remain disordered even at extremely low temperatures due to long-range quantum entanglement. This was one of the first clear experimental observations of that phase, a fundamentally new state of matter observed directly, and that's not incremental. That's foundational physics. If you made it this far, let us know what you think in the comment section below.